The focus of this video is to help us to understand what makes a particular compound aromatic or anti-aromatic. Before we get into that, we have to know that back in the 19th century, scientists actually classified compounds into two groups, either being aliphatic or aromatic. And for the aliphatic category, we have alkenes and alkynes with their derivatives there. And for the aromatic compounds, scientists actually place compounds with unique cis carbon rings and those that have pleasant smells into the aromatic category. But in the early days of the organic chemistry, this classification actually made sense because many of the aromatic compounds came from fragrant oils that were found in plants. But as science progressed, we learned that aromaticity is more about a molecule's electronic structure rather than its smell alone. And one interesting thing is that not all aromatic compounds actually had those pleasant smells. For example, aspirin, one of the most common medicine, contains an aromatic ring, but interestingly, it has no smell at all. So that makes it clear that certain compounds qualify to be aromatic compounds but actually do not have pleasant smells. So look at the rules that were needed for a compound for it to be classified as either aromatic compound or an anti-aromatic compound. I will start our journey by considering the structure of benzene ring, which itself tends to be an aromatic compound. Benzene was actually discovered by Michael Faraday in 1825, and the surprising formula of benzene is C6H6. And it's obvious that the number of carbons is equal to the number of hydrogen. And this makes benzene molecule actually an unsaturated compound. But one interesting thing about benzene molecule is that instead of it being highly reactive, like other unsaturated compounds like alkenes and alkynes, benzene stays very stable, although it is also unsaturated. It is very stable and quite unreactive. So this led scientists to see that there's something actually going on in the structure of benzene molecule, and they think they need to actually dig deeper to see exactly what was happening. After studying the unique structure of benzene and other aromatic compounds of the time, scientists came up with 3 unique rules that if a compound actually meets all of those rules, the compound qualifies to be an aromatic compound. And here are the rules. Rule number 1, the compound must be cyclic. This means that the compound must be in a form of a ring. That is, it should be a closed loop, like a bracelet, where all the carbon atoms are connected in a continuous cycle. So we do not want any open chain compound. So the compound should be closed, a closed ring structure. So if the compound is cyclic, then we check the first box. Then we move on to check if it meets the second rule. And the second rule is the compound should be planar. And when we say a planar molecule, we are referring to a flat molecule, just like a sheet of paper. The compound should actually be flat. And this means that all the atoms in the ring are actually aligned on the same plane. None of the atom is actually sticking out of the plane. So let's take another look at our benzene molecule to see if it is planar or not. So if you take a very close look at the 3D model animation we have on the screen, which represents the structure of a benzene molecule, you will see that it is actually flat or planar when viewed from the side. This is what we mean by a molecule being planar or flat. If I draw a single line through, you will see that it will actually cut through this benzene molecule. Let's contrast that against another molecule, which is cyclooctatetraene, which happens to be non-planar. If we view this molecule also from the side, you realize that it is not planar because it is not flat. Some of the atoms actually stick out from the plane. And if I draw a single line through, the line doesn't cut through all the atoms present. So that is what it means when we say a compound is planar or non-planar by looking at the 3D model. Rule number 3. The compound has to actually follow the Huckel's rule of 4n plus 2 pi electrons. What that means is that there should be a total of 4n plus 2 pi electrons present in a molecule for it to be considered an aromatic compound. And this n here doesn't stand for the number of pi electrons. It stands for just a whole number starting from 0. So 0, 1, 2, and above. So what that means is that we have to use the Huckel's rule, which is 4n plus 2, to find the possible number of pi electrons that if a compound has, it can be considered an aromatic compound. So we have to start the n value from 0. If n is 0, we have 4 times n plus 2. That should give us 2. If n is 1, we have 4 times 1 plus 2. That should give us 6. If n is 2, we have 4 times 2 plus 2. That should give us 10. So what this means is that if a certain compound has 2 pi electrons, 6, 10 pi electrons, then that compound is actually an aromatic compound. That is, if the compound is cyclic, planar, and has this number of pi electrons, then the compound fits to be an aromatic compound. So let's take a second look at our benzene molecule. Benzene is a 6-carbon compound that is closed. We've already seen that it is cyclic and planar. Now, benzene has alternating single and double bonds. From the look of the structure of benzene, we see that it has 3 double bonds. And one fact about double bonds is that for double bonds, one of them is actually a pi bond and the other is a sigma bond. So if we have one pi bond there, so that means we also have pi electrons. But one interesting fact is every bond has 2 electrons present. So if we have 3 double bonds present in benzene, that means we have 3 pi bonds present in benzene. And if each bond contains 2 electrons, that means we have 2 times 3 pi bonds. That gives us 6 pi electrons. So benzene has 6 pi electrons. Now, how do we know about the Huckel's rule? For a compound to be aromatic, it should follow 4n plus 2 pi electrons. And when we did the calculation, we realized that if the number of electrons are 2, 6, 10, in that order, then the compound is aromatic. And benzene has 6 electrons, and 6 is also part of those numbers. So that means benzene is really an aromatic compound. So let's check the boxes again and see. Benzene is really cyclic, it is planar, and then follows the Huckel's rule. So that makes benzene an aromatic compound. What about anti-aromatic compounds? Well, these compounds are also cyclic and planar, just like aromatic compounds, with just one difference. They do not follow the Huckel's rule of 4n plus 2 pi electrons, but they are exactly 4n pi electrons without the plus 2 part of it. So for this also, the n stands for integer starting from 0. But interestingly, for anti-aromatic compounds, we do not want n to be 0, but preferably it should start from 1, because if n is 0, that means 4 times 0 should give us 0. That means there are no pi electrons present, but that shouldn't be the case. So let's check that out for anti-aromatic compounds following 4n pi electrons. So if n is 1, that means 4 times 1 should give us 4. What about if n is 2? 4 times 2 is 8. If n is 3, 4 times 3 is 12. So that means the pi electrons are in the multiples of 4. So that is the case for anti-aromatic compounds. Their pi electron counts are 4, 8, 12, 16, 20 in that order, in the multiples of 4. This arrangement of electrons makes anti-aromatic compounds quite unstable and reactive, unlike the aromatic compounds. So let's pick an example of an anti-aromatic compound and see. The example we'll be picking is cyclobutadiene. It is a 4-carbon ring with 4 pi electrons. How do we know that? Well, before we check the number of pi electrons, let's look at the other two rules. It is clear and obvious that cyclobutadiene is actually cyclic and it is planar from the structure we have. But instead of following the 4n plus 2 rule, which is the Huckel's rule, it rather follows the 4n rule. So cyclobutadiene has 2 double bonds. That means we have 2 pi bonds, and each of the bonds contains 2 pi electrons. So how many pi electrons do we have in total? We have 2 times 2. That gives us 4 pi electrons. So that means for cyclobutadiene, there are 4 pi electrons present in there. If we check it against the number of electron counts that should be present in a molecule to be considered as anti-aromatic, we have 4, 8, 12, 16, and so on. So we would see that the 4 is actually present. So that means cyclobutadiene is actually an anti-aromatic compound because, first of all, it is cyclic and planar, and then it has 4 pi electrons, which follows the 4n pi electron rule. So that means this is an anti-aromatic compound. So in conclusion, understanding aromaticity comes down to 3 main rules. If a molecule is cyclic, planar, and follows the 4n plus 2 pi electron rule, then it is aromatic and then stable, just like benzene. But if it is cyclic, planar, but follows the 4n pi electron rule, then it's anti-aromatic and therefore unstable. So thank you very much for tuning in, and I hope this cleared up the mystery of aromatic compounds. If you enjoyed this quick chemistry breakdown, hit the like button and subscribe for more. See you next time. And remember, chemistry is all about finding the right fit, just like aromaticity. So stay curious and keep exploring the wonders of molecules.